Now let's talk about Newton's first law. Newton's first law is known as the law of inertia. So some people will call it, they'll say Newton's first law is the law of inertia. And that kind of lets you know what's going on. So an object at rest stays at rest. This is the premise of Newton's first law, is that an object at rest stays at rest, and an object in motion stays moving unless acted upon by a force. And then we want to go ahead and define inertia. And inertia is the tendency of an object to remain at rest or to keep moving when already moving. Okay, so I like to tell students that inertia is why you do not want to wake up in the morning, because you are at rest and you want to stay at rest, and it takes a force, sometimes what seems like a superhuman force, to get you out of bed in the morning because of Newton's first law. If you guys get a chance, there's a picture on the internet. It's like a truck. It looks like a semi-truck. And it's got this giant like cement block like crashed into it. And it says inertia. The car stops, but the giant hunk of stone in the back does not. It's really funny. Remind me to show it to you in class because it's really funny. So Newton's first law is the law of inertia, or an object to stay at rest to stay at rest, or an object in motion to stay in motion unless acted upon by a force. You guys, you can actually try this in the hallway at school. Wait so I can supervise you, because I don't think they want you running down the halls. But if you try and you start running from my door and you try and stop at Miss Durden's door, unless you start slowing down before you get to her door, you're not going to be able to stop just at her door. Okay? But if you keep going the same speed and then you try and stop immediately at her door, you can't do it, and you'll run past the door, and that's basically Newton's first law in action right there. In Newton's second law, the definition is basically a formula. And so it says the force acting on an object equals the mass times the acceleration. So we usually show it as F equals ma, but sometimes the book shows it as A equals your force over your mass. And you can put this formula in the triangle. This is not a very good triangle. But you'd have your F on the top because it's separated, and your mass times acceleration are next to each other. So you need to put your mass and acceleration next to each other in the triangle right there. And the unit of force is newtons. And so whenever you have a force, it's going to be in newtons. If you ever see anything in newtons, in a word problem or anything, they're talking about the force. And here's the conversion. 1 newton is equal to 1 kilogram times meters per second squared. And we'll work out a problem and you'll kind of get to see how that conversion works. And so basically, your acceleration depends on your force and also the mass. So the bigger you are, the more force it requires to get the same acceleration. And if you're something very small, you can accelerate very quickly without having to have a lot of force. Newton's third law states that for every action, there's an equal and opposite reaction. And we say that forces always occur in pairs, and these pairs act in opposite directions. So the typical example for this is a guy shooting a gun, and you can see his action is this bullet coming out of his gun, and the reaction is that recoil that pushes him back. I like to use the example, when I was a kid, my sister would kick me in the shin, and I couldn't help it. There was this reaction to me kicking her back in the shin, and I totally couldn't help it. It was just Newton's third law in action. So that's an example I like to give. My parents would say, you shouldn't kick your sister, and I would say, but I can't help it. I didn't know about Newton's third law, but if I did, I totally would have used that. Newton's third law also helps explain our free body diagrams. So basically, if you have a force, let's say that you're shooting a gun this way, and your force is your gun, your bullet going out of your gun, and then you're going to have a recoil that is equal and opposite. Now, the reason that you don't move as far back, you don't move the same distance back as the bullet moves forward, is because you have a lot more mass than the bullet. And so, since your force depends on your mass, you're actually going to accelerate backwards slower than a bullet. It would be really, really bad if you accelerated backwards as fast and as far as the bullet. It would make guns not really all that useful.